1.2 Cellular mobile communication. The case where a telephone is fixed to a specific location was referred to as fixed-line communication. On the other hand, being able to carry a telephone and talk anywhere is called mobile communication. In order for mobile communication to be possible, the telephone must be able to move. Of course, one might argue that a telephone with a very long cord could be carried here and there, making it mobile communication. However, since that cord cannot be extended to the neighborhood supermarket or to a school in another region, it is difficult to call such a telephone a mobile phone. That being said, since it cannot be said that a mobile phone's coverage area extends to every single region, it would be more appropriate to define mobile communication as a communication method where the subscriber line is connected wirelessly and mobility is managed. To receive a call in the kitchen from a phone located in a large room, the phone line must be wireless. This is the so-called cordless phone. Prior to the development of mobile communication, communication systems emerged that connected the telephone and the exchange wirelessly. More accurately, this takes the form of a cordless phone where the telephone base and the handset are connected wirelessly. Taking this a step further, the wireless range is expanded even more, extending not just to the kitchen, but to the front of the elevator, and further out to the parking lot. By making the radio frequency output between the base unit and the handset sufficiently strong, it is possible to enable calls even dozens of meters away from the house. This allows for wireless calls within the range of the base unit's power, that is, within the base unit's coverage area. Now, we can conceive of the extended cordless telephone. One can imagine a separate device called a repeater that functions like a telephone base unit, connecting both to a portable wireless terminal and to an exchange. If this repeater is a system with a much higher output than the typical telephone base unit we have considered so far, wireless calls become possible within the repeater's coverage area. For instance, if such a repeater is installed on the roof of an apartment building, all telephones wirelessly connected to it can make calls. Not only in the living room or bathroom, but also in areas like the apartment parking lot or shopping center. Anywhere within the repeater's coverage area, users can move around freely while talking. This method corresponds to the pager, also known as the BB, which was popular from the late 1980s through the 1990s, and the city phone service, which was briefly commercialized just before the launch of PCS. The pager broadcasts simple messages, later understood as short text messages, within a coverage area, enabling city phones within that area to establish a call connection. Here, broadcasting is distinguished from communication. While communication continuously manages and confirms whether a transmitted signal has been received or maintained, broadcasting does not manage these aspects. This is also related to service fees. In the case of communication where reception must be continuously confirmed or maintained, fees are collected based on the volume of telephone traffic, whereas for services like Wi-Fi, a form of communication independent of confirming or maintaining reception, a flat-rate pricing system is adopted. The limitation of the city phone is that while communication is possible while moving anywhere within a repeater's coverage area, the call is disconnected once you move outside of that area. However, the coverage area cannot be expanded indefinitely. The repeater performs the role of receiving the telephone signal, also called a call, that a subscriber must receive from the exchange and delivering it to the wireless telephone. This connection is only possible for telephones located within that specific repeater's coverage area. If the subscriber who needs to receive that signal is outside the repeater's coverage area, that subscriber cannot establish a call connection. In order to be able to make and receive calls from anywhere, a signal must be received, even if one is outside the coverage area of a specific repeater. For this to happen, the repeater requires a function to pass that signal to the repeater where the subscriber is currently located. Here, a subscriber refers to a person carrying and talking on a mobile phone. To achieve this, it must be possible to identify at all times which repeater the subscriber's mobile phone is connected to, and the corresponding call must be transferable to the repeater where the subscriber is situated. In other words, the functions of the mobile telephone system we envision must include managing the subscriber's whereabouts, and a handoff function that transfers the call connection to the repeater, toward which the subscriber is moving so that the call can be maintained continuously. Furthermore, all of these connections are made wirelessly. In this regard, a mobile switching center requires additional functions beyond the traditional switching functions of connecting or disconnecting calls, and the routing functions of establishing PES for call connections. Specifically, it needs mobility management functions to track the whereabouts of mobile phones and hand over calls, as well as wireless connection capabilities. The mobility management function must mediate between the base stations responsible for wireless connection, so it is generally performed by a base station controller. Furthermore, the coverage area of a base station is called a cell. To establish a mobile communication coverage area across a very vast region, such as the entire territory of South Korea, the whole area is filled with a multitude of cells that each have a relatively small coverage range. By enabling the transfer and receipt of a moving subscriber's call between these cells, the entire area composed of those cells can be used as a coverage zone. This method of communication based on cells is called cellular communication, and a cell-based mobile communication network is called a cellular mobile communication network. Additionally, the procedure of transferring and receiving a call between cells is called handoff. 1.2. 1. Base station and cell. To satisfy the requirement that the user's location or the terminal's location must be mobile, the subscriber line between the switching equipment or relay equipment must inevitably be wireless. Therefore, a representative new technology in mobile communication is the wireless connection between the terminal and the base station. The connection between the terminal and the base station is also referred to as the air interface. A representative wireless access technology is a wireless interface standard such as TIA IS-95, which is based on CDMA technology. Among North American wireless interface technologies, there was also the IS-54 standard based on the TDMA method, but this mostly disappeared alongside the advancement of IS-95. Before discussing cellular communication, I will first talk about radio broadcasting, which has limited communication coverage. Broadcasting stations like KBS or MBC set up large, tall transmission towers in high-altitude urban areas such as Namsan to transmit radio signals throughout Seoul, emitting broadcast signals with very high power. The transmitted radio waves undergo attenuation as they propagate. Theoretically, in free space, the signal attenuates in proportion to the square of the distance. However, in urban areas with relatively many buildings and obstacles, the degree of attenuation is more severe, so the signal generally spreads while attenuating by the fourth to fifth power of the distance. In other words, the transmitted signals are received weakly in suburban areas far from the transmission tower on Namsan, such as Gwangmyeong, Guri, and Sungnam. To ensure that people living in Guri can also receive the signal, the output power of the transmission tower would have to be increased. However, there are various difficulties in raising a transmission tower's output. A high-output transmission tower requires transmission equipment with greater volume and heavier weight. Additionally, the power consumption of the transmission tower increases. Furthermore, while the signal would be received with sufficient strength in the outlying areas, an excessively strong signal would appear in the areas immediately adjacent to the tower, such as the Hwandong neighborhood in Yongsan-gu. To resolve the issues where excessively strong radio waves appear in areas near the transmission tower, and excessively weak waves occur in outlying areas like Guri, a solution must be found. Furthermore, the overly bulky and oversized transmission towers themselves also pose a problem. To address these issues, one method is to establish a new transmission tower on high ground in the Guri area, such as a Chosin, thereby creating a new communication coverage zone. Of course, the broadcasting station must simultaneously send the same broadcast signal to both the Namsan transmission tower and the Achosin transmission tower. The Achosin tower will significantly improve the reception status in the Guri area. Furthermore, the intensity of the broadcast signal, which was excessively strong in the area surrounding Namsan, can be somewhat moderated. By erecting an additional transmission tower, large output transmitters can be made smaller, and the signal strength can be smoothed out to some extent. Figure 1-6 shows that by setting up several small-scale transmission towers, the signal strength within the coverage area is distributed evenly. Now, let us consider the case of mobile communication. In this scenario, the broadcasting station's transmission tower can be thought of as a base station. Furthermore, a broadcast reception device, such as a radio, corresponds to the subscriber's mobile phone. Using small-scale base stations in mobile communication provides a much greater advantage than simply reducing the weight of a broadcasting station's transmission tower. Unlike broadcasting, a user's terminal not only receives signals from the base station, but also transmits its own signals back to it. If there were only one base station in the entire city of Seoul, subscribers in Gwangmyeong or Guri would need to send their signals all the way to Namsan where the base station is located, which would require a very high power output. Needing high power means a large device is required, and it would be difficult for a person to carry around such a bulky mobile phone. Therefore, the method for securing a coverage area in mobile communication should not rely on a single large base station with a massive communication range, but rather on communication based on cells formed by multiple base stations with low power outputs. However, this method presents a new problem. Since multiple base stations are used to secure the entire coverage area, overlapping regions occur where the outputs of the base stations interfere with each other. When a transmission tower broadcasts signals unilaterally, setting up several small power towers was not an issue. However, because multiple base stations each generate their own output zones, overlapping power regions are created. Of course, even if the output of the base stations is relatively low, the problem of overlapping outputs still persists. Unlike broadcasting, a mobile phone must transmit its own signal and aim for a specific base station, but the base station the phone should target becomes ambiguous. This phenomenon is called far plus, and it becomes a critical factor that mobile communication cell planning technology must resolve. In the case of mobile communication, using base stations which are relatively low power transmission towers offers the advantage of being able to reduce the size of mobile terminals such as smartphones and cell phones. However, because multiple base stations each output their own signals, the far plus phenomenon, which is a signal overlap phenomenon, can occur. A mobile phone, as a mobile communication terminal, selects the base station with the strongest received signal for transmission and reception. However, in a situation where far plus occurs, a problem arises where it becomes difficult to select a base station. In other words, it is difficult to find a base station that outputs a distinctly strong and sustained signal. Cell planning is a critical technology for effectively deploying base stations. It is difficult to precisely determine the exact range of a base station's signal propagation, or the radio waves transmitted from a mobile phone toward a base station. Therefore, cell planning must determine the size of a cell by considering both the forward link, which sends signals from the base station down to the terminals, and the reverse link, which sends signals from the terminal up to the base station. For reference, the forward link is also called the downlink, and the reverse link is called the uplink. These terms were originally used in satellite communications. Downlink referred to the link coming down from a satellite to a ground station, and uplink referred to the link going up from a ground station to a satellite. These terms are used metaphorically to describe signals coming down from a base station to a terminal, and going up from a terminal to a base station. To perform cell planning, the shape of the cell must be modeled. In general, since radio waves have the characteristic of radiating in all directions, in vast rural areas like open fields, the cell boundary would take the shape of a hemisphere centered on the base station. On the other hand, in urban areas crowded with buildings, the boundary will not form a smooth circular shape like in rural areas, if one considers the areas where the base station signal cannot reach. Due to shadowing effects, while one might consider a circular cell, cells are not perfectly circular, which presents a difficulty. Ultimately, since the shape of a cell is modeled in relation to cell deployment, the shape of a cell is explained according to the relationship between one cell and another. While various cell shapes could be established, a hexagonal cell resembling a honeycomb is generally considered the standard spatial structure, as it can fill the entire space without gaps. In this case, a single cell is surrounded by 6 most adjacent cells, followed by 12 next most adjacent cells, and so on. How, then, is the size of a cell determined? The size of a cell is determined by the output power of the base station. The base station transmits signals at a constant power level to create a specific coverage area. Generally, what we call a coverage area refers to a signal strength at which a terminal can receive the base station's signal and demodulate valid information from it. Being able to demodulate a valid signal means a signal strength where, for example, only one frame error occurs out of 200 received frames. This level of signal strength is approximately 0 for picowatts. In other words, the distance at which the base station's signal attenuating as it spreads through space reaches the level of 0 for picowatts, is set as the base station's coverage area. If we assume that the Gangnam base station, installed in the highly congested Gangnam station area, outputs for W, and the attenuation constant of this area is N5, the distance at which the signal transmitted by the Gangnam base station reaches approximately 0 for picowatts, that is, the cell radius formed by the base station's output is about 100 meters. Cell size is also determined by movement speed. For example, it depends on whether the focus is on pedestrians moving at relatively slow speeds or on cars moving quickly on a highway. Moving fast means that handoffs between cells must occur frequently. However, if the cell size is larger, handoffs between cells will occur less frequently. In reality, since the speed of the processor handling the handoff is limited, the cell size must be made larger to keep the number of handoffs within the processor's processing capacity. Additionally, if the moving object's speed is slower, the frequency of handoffs decreases, even for cells of the same size. In other words, even with the same handoff frequency, if the speed of the moving object is slow, the cells can be designed to be smaller. In the early days of PCS, the system was designed specifically for low-speed pedestrians, so the cells designed at that time considered sizes as small as picocells or even nanocells. As the cell size became smaller, the subscriber capacity that could be accommodated per unit area increased. In other words, because the number of subscribers grew, mobile communication services could be offered at a lower cost. It was a form of small margins, high volume. For this reason, PCS was described as an affordable communication service that all citizens could enjoy. 1.2. Frequency reuse. We have studied that a cellular mobile phone system is a method of communicating by dividing a wide area into small cells. In this section, besides this, I will talk about the capacity of cellular systems. Through the frequency reuse factor, the small cells of a cellular mobile communication system must use different frequencies because they possess distinct coverage areas. In this regard, frequency can be understood as a finite resource that is not infinite and must be divided and shared. Consequently, a new paradigm regarding capacity emerges, the need to use limited frequency resources more efficiently. Let us assume a completely isolated cell A and another isolated cell B located a certain distance away from it. Both cells are transmitting signals modulated at the exact same frequency. A terminal belonging to cell A receives only the signal from the base station in cell A. If that terminal moves toward the edge of cell A and eventually leaves the cell, it can no longer receive even that signal. However, as the terminal moves further away from cell A and enters cell B, it begins to receive the signal from cell B. But what if, in this story, the distance between cell A and cell B is very close? In this case, even if the terminal belongs to cell A, it will receive the signal from the cell B base station as well, resulting in interference. However, if cell A and cell B are separated by a long distance, this problem does not occur. In such a scenario, even though the base station signals of cell A and cell B use the same frequency, they do not interfere with each other. Therefore, if the two base stations are sufficiently far apart, they can use the same frequency. The distance between base stations is related to the size of the cell formed by the base station's output power. By determining a distance at which interference between cells in a mobile communication system is negligible, the same frequency is reused. As the demand for communication increases, it becomes extremely important to improve the efficiency of utilizing given frequency resources. Therefore, the frequency reuse rate becomes a very significant advantage of that system. Figure 1-7 shows cells where frequencies are being reused. Returning to the story of the isolated cells, if cell A and cell B can use the same frequency because of the distance between them, we can set the area where the terminal has left the range of cell A, but has not yet entered the range of cell B as a region that uses another frequency. To summarize, we can imagine that cell A and cell B transmit signals using the F1 frequency band, while the intermediate area between them transmits signals using the F2 frequency band. For example, if the total given frequency bandwidth is 2.1 MHz, and the bandwidth that must be allocated to each communication channel is 30 kHz, the total number of communication channels available from the total frequency band is dividing 2100 by 30 equals 70. When applying this to a cell structure arranged as in figure 1-7, with cell A at the very center, you can distribute 10 different communication channels to each of the surrounding cells, from cell B through cell G, using distinct frequency bands. Since at least these 7 adjacent cells do not use the same frequency, there is no frequency interference. A group of cells that divide the total frequency among themselves without overlap, ensuring that no adjacent cells use the same frequency, is called a cluster. In figure 1-7, the red-colored cells form a single cluster. In this case, the 7 cells within the cluster are considered to be free from significant interference from cells outside that cluster. The frequencies used in cells A through J of the red cluster are then reused in cells A through J of the blue cluster, respectively. A high-frequency reuse rate increases the available capacity of a communication system. Therefore, the degree of capacity increase can be indicated by the frequency reuse rate, representing the system's frequency reuse performance. We can define the frequency reuse factor as an indicator to express this frequency reuse performance. Since this is expressed as the distance at which interference between cells can be neglected, it is achieved through a geometric analysis of the hexagonal cell shape. To facilitate frequency reuse, we must find a way to represent the distance between these hexagonal cells. To this end, we can consider a new coordinate system, as shown in figure 1-8. Unlike the familiar Cartesian coordinate system, this new coordinate system is an oblique coordinate system where the coordinate axes, u and v, maintain an angle of 60 degrees. The unit length for each axis in the u-v coordinate set corresponds to the case where the radius of the hexagonal cell is square root of 3 times r. The distance to the nearest adjacent cell is defined as a unit of 1, which is square root of 3 times r, and the center of any given cell is represented by an integer pair of u and v coordinate values. In the new coordinate system, the center of a hexagonal cell can be expressed through u and v, as shown in figure 1-8. For example, a location P can be represented by its u-coordinate and v-coordinate values. By calculating the distance between arbitrary points in this coordinate system, we can represent the distance between cells where frequency reuse is possible. Let us calculate the distance d1 to between point P, located at u1, v1, in the new coordinate system, and point Q, located at u2, v2. First, in figure 1-9a, d1 can be obtained as the sum of the squares of x and y, using the Pythagorean theorem. Additionally, the base of the triangle can be found from figure 1-9b. In this case, the hypotenuse of the triangle represents the change along the u-coordinate system, which is u2, u1. Consequently, x is equal to u to cos 30 degrees. Furthermore, y can be obtained through figure 1-9. At point Q, v2 is a value as large as v2 along the v-axis, relative to the u-axis where the v value is 0. This is the same in a Cartesian coordinate system. Therefore, since the value of v is the distance to the point where it meets the u-axis, v2 is the length of the gray line in figure 1-9. Of course, v1 can be obtained in the same way. Ultimately, y is the length of the red dotted line minus v1. Ultimately, by calculating the distance between two arbitrary points from the equations derived above, the distance between the center of the current cell, defined as 0, 0, and the center of a frequency, that is, the frequency reuse distance, can be expressed as in equation 1-1. Furthermore, we can write the frequency reuse factor, k, as shown in equation 1-2. For example, if a cell centered at 0, 0, uses the same frequency as a cell located 2 units along the u-axis, and 1 unit along the v-axis, The frequency reuse factor is 7, as shown in figure 1-10. In this case, the cluster contains 7 cells, and each of the 7 cells within the cluster uses the same frequency as a cell located I2 units along the U-axis, and J1 unit along the V-axis. Frequency reuse distance in sectored cells. A method to further reduce code channel interference without negatively affecting system performance is sectoring. This involves using directional antennas that radiate signals only in specific directions, rather than omnidirectional antennas that radiate the base station signal in all directions. When using directional antennas, frequency interference occurs only in the base stations of the same channel located within the antenna's radiation direction. Therefore, code channel interference is reduced by that amount, and frequency reuse efficiency increases. In the case of CDMA networks, a 3-sector cell is used, which divides a cell into 3 sectors, alpha, beta, and gamma. When 3-sector cells are distributed as shown in figure 1-11, let us calculate the distance between cells using the same frequency. Depending on each frequency reuse factor, the distance between cells relative to the cell radius for 3-sector cells can be calculated by applying the above formula, as follows. Ultimately, sectoring a cell triples the reuse factor of the cells. Therefore, in the case where the frequency reuse factor is 7, the ratio of the reuse distance to the cell radius increases by approximately 73%, compared to an omnidirectional base station without 3. Sectoring. However, considering that the cell radius increases by approximately twofold when using 3 sectors, the actual reuse distance decreases by about 14% instead. Therefore, the results can be summarized as follows. Figure 1-12 illustrates cell cluster shapes with various frequency reuse factors. Assuming a regular hexagonal cell shape, the figure shows the cell layout of clusters for frequency reuse factors of 3, 4, and 7, comparing both omnidirectional and 3-sector cell configurations. Figures 1-12A, B, and C represent the cell layouts for omnidirectional cells, while D, E, and F depict the cell layouts for 3-sector cells. The use of directional antennas, which possess radiation characteristics oriented only in specific directions, reduces inter-cell interference, and thereby increases system capacity. In the case of CDMA, where system capacity is highly sensitive to interference signals, directional antennas and sectoring are critically important technologies. Furthermore, considering that the CDMA system serves as the foundation for mobile communication technology, the development of techniques aimed at minimizing spatial and channel interference such as smart antenna technology will continue to advance in alignment with the evolution of mobile communication.